Okay, so now I want to talk about how do we then quantify the mixtures of when we're not at equilibrium. So you have two conditions, equilibrium and not at equilibrium. So you're either at equilibrium or you're not. So how do we quantify the system's progress when we are not in equilibrium? Well, we know from, so when not in equilibrium, what do we do? Well, we know that the chemical potential is equal to the chemical potential at standard state plus RT log of PA, where, and this is, so standard conditions, and then we've got this is equal to the vapor pressure of A, okay? But we know that this is equal to PA star, so this is going to be the pure P vape of A, and then this is the mole fraction of A. Okay, and it turns out that we, and this is what we did with mixture, so from before, chapter 5, I believe, we talked about delta G of mixing and delta U, or delta mu of mixing, and so that delta G that we would have of mixing, we can also relate to that of, or sorry, not the delta G of mixing, the delta G of reaction when you look at the difference between the final and the initial state gives us delta G of the reaction under standard conditions plus RT log PB over PA. And again, these are the partial vapor pressures. And we get that from, again, looking at the difference in the chemical potential, which is the difference in the Gibbs energy. So we subtract all of this from A and all of that from B. Okay, so we subtract all of that from A and B minus A, and we get this delta G of reaction with P, B, and PA, partial vapor pressures. Okay, but I asked the question, we have two conditions, not in equilibrium and equilibrium. How do we relate equilibrium stuff, i.e. this equals 0, such that you can then say delta G standard is equal to minus RT log PB over PA. So that gives you information about the non-equilibrium, or sorry, equilibrium conditions. But what about the non-equilibrium conditions? Let's find out what parameters we can control or change that will link us to the extent of the reaction. So the question is, what links us to the, God, that looks bad, the extent of reaction? Because we want to know how does it change along this axis. And my point is look at the ratio. So let's define a new idea. Define this ratio, PB over PA is equal to Q, because why not? And I'm going to call this the reaction quotient. Cool? Q is equal to reaction quotient, which is the partial vapor pressures of B over the partial vapor pressure of A. Okay, so what that does is that says then that delta G of reaction is equal to delta G standard conditions plus RT log of Q. And we know, hopefully, that at equilibrium, Q is going to equal K, or the equilibrium constant. Therefore, at equilibrium, delta G standard is equal to minus RT log of K. Cool? This links chemical equilibrium with thermodynamics. All right. So we have two cases then. So here I've got G as a, with respect to the extent of reaction, and I've got, let's say this is for A goes to B. Okay, so I've got pure A, and over here I've got pure B. Actually, let's just say that this is A, and B. Okay. If equilibrium is continuously maintained throughout this, and A and B are basically the same thing, you're going to get something like this. However, there should be a minimum here, and that minimum is going to tell you where equilibrium is going to lie between A going into B. If, however, you have, so if A and B are at different chemical potentials, you will have a driving force, A, B. So Gibbs with respect to extent of reaction. If, however, you have a driving force that there is a different chemical potential between A and B, the system is going to spontaneously go towards the lower chemical potential or the lower Gibbs energy. Okay, so right. So for no mixing, just reaction, you get this line. If you have mixing and reaction, this is where it gets fun. If you have mixing and a reaction, you're going to get something that looks like this. All right, where the delta G of mixing is going to equal RT mole fraction of A log mole fraction of A plus mole fraction of B log mole fraction of B. There should be an N here. And so you'll have then an additional delta G of mixing, an additional delta G of mixing to your delta G of reaction. So this is the delta G of reaction, and then with mixing, you're going to get something that looks like this, such that there's an additional minimum that you can find. Because if you think about it like this, so two of these A's turned into B's, okay? So that's the reaction. But then you're going to have now the reorientation or the mixing. Once that reaction has occurred, now you need to distribute these particles or these molecules such that you've minimized the Gibbs energy of mixing. Cool, so there's an additional minimum that you can find, not just changing delta G, but now mixing delta G. Cool? Okay, so let's take one more step in thinking about what that looks like mathematically, which is where you should always take your ideas. Delta G reaction equals delta H reaction minus T delta S of reaction. So under no mixing, so if you just have this occur, just A's turned into B's, and then nothing mixes after that, this is what you will have. You will have if no mixing occurs, that is what you will have, where this is the delta S of the system and not delta S of the surroundings. So this is for no mixing, and it's a heat-driven process. With mixing, which means now the B's are going to move around, they're going to go down there. Then you're going to have delta G R is equal to delta H R minus T delta S R, and there's going to be an additional mixing component to where you have an entropically driven redistribution of that energy to accommodate getting this minimum portion. Cool? Okay, I hope that made sense. Hooray. The next video, we'll dive deeper into the reaction quotient and K.